Okay, thanks. Okay, to start with, anyone with any questions? Nope. Okay, so firstly, I guess, again, my apologies a little bit, but the way departments schedule the discussion sections, one discussion section takes place in between sort of two lectures. So those of you who were in yesterday's discussion section, you kind of peeked ahead a little bit into material that I'm covering today. Hopefully, in a week or two, we'll settle in a rhythm. But I didn't want to go make the discussion go waste. The other thing is, hopefully you are set up with Logisim. In case you're still running into problems, I think one of your peers was very generous to share the Windows installation. So thank you, whoever you are. The Mac one, my instructions had a little bit of a typo, but again, we caught that. I think unfortunately, yeah, there are myriad versions of these operating systems, and also some of you with older versions may be running into problems. It seems like one student was on the Mac side. So come and seek our help. Generally speaking, if you need help with Mac, then I'm your person. If you need help with Windows, the Jicheng, the TA for one of the TAs, he uses Windows. He can assist you. Unfortunately, I have kind of close to zero knowledge of Windows. Okay, so here. Okay, so today's lecture is really about considerations that go into representing information digitally. Some of it is intuitive. If you've done a programming course, some of these concepts would be natural, but it's still good to think about it, and particularly because when we are dealing with things in the hardware side of things, considerations are a little bit different. Okay, so so as we kind of talked last time, digital systems have inputs which are discretized in time, as in we sample them, discretized in value, as in we assign some finite set of bins. So it's a set of finite values. And a special case of it is binary input. That's what we deal with. Our computers currently, by and large, are designed using a discrete set of two values. And there are sort of rational reasons for it. Having two values is very robust, right? I mean, high, low, you don't have to worry about anything else. But having said that, there are computers, there are digital systems which use other bases, 3 values, 4 values, whatnot. And binary is dominant very much, but it's not necessarily the only thing. And we are going to talk, I guess the main takeaway from today's lecture is this particular module is really what makes for a good way of encoding information. Okay, so let's start with that. I'm going to just skip some of this stuff. Okay, so digital systems, kind of the main thing is that the values come from a finite set, right? And that finite set could be anything. Now, generally speaking, what happens is a system that you're designing its input would be some set of values, even some finite set of values, even things like integers, let's say, right? I mean, so our computers are not designed, generally speaking, to deal with an arbitrary open set of integer values. So like you may have, let's say, a computer which can represent, let's take an example. Let's say I may have a computer which uses 8 bits for integers. That means it can only represent 256 distinct values. And so that would be the set. Our current computers, anyone, how many bits do they use? When you program them? Like what's the size? What's the number of bits used to represent integers when you program currently? Yeah. 64-bit is pretty much kind of the norm. If you have an older computer, maybe 32-bit. So that means you have 2 to the power 64 distinct values. And one of the things is in that, we'll see later in the course, you have to squish negative values, positive values. So there are different conventions for doing that and doing that representation in a manner which makes hardware simple. Now, so like normally when we think of just base 2 numbers, we kind of just think of if I give you some particular 8-bit number, then we think of it as the corresponding positive integer value. But of course, we do arithmetic with negative numbers, and also we have to find some ways of representing things. More generally, we may maybe not even be dealing with numbers. By the way, sort of real numbers are even more complicated, right? I mean, in mathematics, you have a infinite set of infinitely dense set of real numbers, right? In between any 2 real numbers is another real numbers. Of course, we can't represent it. So again, we find some clever ways of representing certain values on the real number line into a finite set, and then we do arithmetic in that. So like, for example, if you work with C++ and all, you have these things like float and double and all, right? These are different ways of representing what is otherwise essentially a continuous number line into a discrete set. But some other things are much more natural, right? I mean, if I have a sensor measuring the state of the door, open, close, it's obviously discrete. Or for example, if I have something which is, let's say, dealing with cards and playing card deck, by definition discrete. So a lot of things sort of come intrinsically discrete, and we kind of figure out ways in which we take the set, and then if our computer is binary valued, then we kind of find ways to represent it in some bits. So really what's going on is kind of a 2-stage structure, right? Often we start with analog values, we discretize them, we get a discrete set, and then we find a way to map those discrete values into bits if our computer is a binary computer, as most of them are. Okay, so the other thing to remember is that, again, sort of in this general picture, sort of starting out is some arbitrary physical quantity of interest, so that's fine. Eventually, sort of when we map it into the input signal, right? So I was saying bits. So our electrical computers tend to be 0, 1, 2 values, but it doesn't need to be electrical. And in other, there are, as I mentioned this time, there have been mechanical computers and chemical computers, and actually UCLA did a lot of work, right? Right across from the science squad and chemistry department on molecular computing. People kind of represent any physical phenomenon which you can have somehow represent a discrete number of states in. You can harness it potentially as a computing system. So if you go back and look at some of the historical things, so like, for example, Alan Turing, kind of the father of computing, if you may, right? So he was famous for using computing to break codes, the German codes during World War II. And if you go to this kind of nice little museum at Bletchley Park and near Oxford in UK, which is where he did most of the work. So his computer for doing this was kind of, you can, in modern terms, you can say it's a computer which was a fixed program computer, as in it ran one particular program, but you could configure it for the code you were trying to break, and it was an electromechanical computer. Okay, so you kind of see out here in this picture that he has these dials and all. They actually have kind of these numbers, so you kind of configure things, so they're discrete valued. These are electrical. Remember, this is in early 1940s, late 1930s. So transistor wasn't even there. So these things were designed using mechanical relays and stuff like that. So pretty cool stuff. If you're ever in UK, visit it. I think it's just absolutely fascinating. If you go back even more in history, there have been purely mechanical computers also. So arguably the very first programmable computer was by Babbage. And this is purely mechanical. Essentially, the digital part comes from gears having a fixed number of teeth, and you kind of program things using that. And in fact, he had kind of very detailed plans for the computers and all, and replicas of it starting in, I guess, I don't know if I have the dates in these slides, but yeah, late 1990s and all, they built and sort of showed that they actually worked. And also these were programmable, and actually the first programmer for computers was Ada Lovelace, and she I guess in her honor, in some level, there are a lot of things in computing named after her, including a programming language called Ada, which was very widely used in 1980s and 1990s for Department of Defense type programming. And also there's kind of a lot of history on that regard, and you can find a lot of stuff. So yeah, first programmer, Ada Lovelace. So sort of underpinnings of computing, digital logic, the ability to program these things predate Turing, but what Turing brought was a mathematical rigor to it. And contemporary to Turing, there were a couple of other people in 1930s who got a lot of laid a lot of foundational work. One is a guy called Gödel, and there's a prize called Gödel Prize named after him. And then there is also someone called Church. Church and Turing, I think Church was Turing's advisor, if I'm not wrong. But in any case, they kind of gave two equivalent but different ways of looking at the mathematical foundations of computing. And in a sense, they help define what does it mean for something to be computable. Okay, so, and Turing had this abstract machine called Turing machine. Back to sort of days of Babbage and Ada Lovelace. At that point in time, these were very early days of computing. There was no mathematical theory, but these people were sort of showing that that they were developing these notions of programming and creating a functional computer. And Babbage failed to build it, but like I said, in 1990s, they actually created a replica. So that's kind of history. And actually, interestingly, right here at UCLA, I think I had some slide again in 1940s. There was a lot of development of sort of computers, including electromechanical computer. So basically, in World War II time, a lot of technologies were advanced, including computing things. Also, I mean, now we associate Silicon Valley with computing, but actually the first computer in California was right here in LA, again for defense purposes. Anyone knows where the first computer was made, first electrical computer? That's where? No, it's at UPenn. Yeah. So if you go to UPenn's electrical engineering department, and kind of when you enter, a big thing, and that's the first electrical computer, again related to defense applications. So it was for calculating missile trajectories. Okay, so anyway, a lot of stuff, and there's some controversy over it. France lays some claim over it. UK, Manchester, I think they lay some claim over it. So like with a lot of these things, just like with aircraft and all, there are a lot of competing claims. So you could say maybe collectively they were the first. Okay, so now back to our thing. If I'm trying to represent information digitally, namely in a discrete manner, a question naturally arises is that will I lose information, right? The world is analog. If I'm going to map it into this discrete set, does it mean I'm losing information? And I alluded to it on Monday that under certain conditions, we don't. So conceptually, what's happening is I have this waveform, right? This guy. And I want to convert it into discrete values. And also, when I'm converting discrete values, I also have to discretize time because I'm going to deal with sort of just a set of values, different values for different time instants, and also the values themselves need to be discretized, right? So what happens out here is I have to have some strategy for deciding at what instance in time do I measure the value. And then the other thing is, once I measure the value, I need to map it into certain finite number of bins, right? So, kind of intuitively, you might say, okay, if I sample it more frequently, then I probably have less information loss, stands to reason. And likewise, if I sample it more finely in terms of the value, let's say if I'm measuring the value, if instead of dividing it into 10 bins, I map it into 100 bins, I will get a more fine-grained representation. Both of these things intuitively stand to reason. Now, let's talk about what are the implications on these two sides. So whenever we sample a signal in this manner, right, and sample some physical quantity in this manner, I need to have an associated way of reconstructing from those digital values, right? I give you a set of digital values, reconstructing the original continuous waveform back in principle, right? So I should be able to, once I give you values at these time instants, in this case, right? Let's say these instants, and then so now you'll have a finite set of values, and then each value itself, like this value out here, is discretized, right? So I have to map it into one of possible things. So for example, I may divide these things into certain bins, and then the value for each bin can have a identity, and then we map it to that. And a question which becomes is that if I give you such a set, can I reconstruct the original signal back? If I can do it successfully, then there is no information loss. If I fail to do it, there is some information loss, and then how much information loss is there? So long story short, back in, my apologies, I'm working with PDF. So back roughly around 100 years ago, this guy Nyquist and a little bit later Shannon, they kind of formalized this notion that if I know one thing about a signal, the analog signal, namely what is the highest frequency component that exists in it. So if in math, you learn about Fourier transform, right? So I can take any periodic, any signal, and I can decompose it into, I can do its Fourier analysis. Essentially, I can think of it as a summation of sine waves, very crudely speaking. And so now you can say, okay, what is the highest frequency sine wave, which needs to be part of that combination? And then what Shannon Nyquist said was, if you were to, if this gap out here was 2 times F max, where F max is the highest Fourier component, highest frequency component in that if I were to do it, and I was measuring these values very accurately, then I can reconstruct the original signal back. By that, what I mean is, if I were to ask you the question, what is the value out here? Then just given that finite set of values, I can reconstruct. Okay. So those of you who are in E, in your signal processing classes, you may have already encountered it, or you will encounter it. But in this case, what we're basically saying is, if my signal has a well-defined highest frequency, I can reconstruct it.
And this we use for regression. What is that?
No. Regression is kind of an entirely topic. We can talk offline, but short answer, no. I mean, you can of course do regression on discretized values. That's how we kind of do it. But if you step back in 1940s and 50s, there were such things as analog computers, and there, without sampling, you could do computation. You can multiply values, take their exponentiation, do algorithms, right? I mean, that's and nowadays in quantum computing, there's something similar happening. But ignoring all of that, what this basically says is, I can take a real world signal, I can map it into a discrete set of values, and then I can do my computation on it, and then I can go back whenever needed to the original signal. So there's no information loss, provided this requirement is met. And then since then, in recent decades, there's a lot of very cool advancement which has happened, which has shown that if I know more about this signal, this blue waveform, then I can actually sample even more parsimoniously, more sparsely. And in fact, a lot of cool work on that again happened right here at UCLA in the math department. There is this very famous professor, Terence Taub. Some of you may have heard of him because he's he's a Fields Award, Fields Medal winner, which is kind of the Nobel Prize in math. And so he, and together with a couple of other people, someone from Caltech, I think, they kind of came up with this idea of a compressive sampling. So they basically can, loosely speaking, they can sample a lot less, but they need to know something more about the signal, about the underlying property. So a lot of clever math has kicked in. For purposes of those who design digital systems, it doesn't matter. There's some strategy which can take the signal and which can map things into a finite values at finite time instants. That still begs the question, what about the value, right? I mean, how many bins should I divide? Right? And again, intuitively, if I divide it into more bins, then I'm better off. Now, this is where another concept comes in, which is, I don't think I have any slides on it, but how fine that bin should be. Okay, so now if you think about it, let's say this signal out here is lying in this bin. So when I map it into a particular bin, all values in that bin are going to be mapped to the same bin number. So that there is an error being introduced, and it's referred to as quantization error. Because what we are doing is we are taking a continuous value and I'm dividing it into a finite set of values, and therefore there will be an error which corresponds to kind of the size of the bin, loosely speaking. And that to you would be visible would seem like some sort of a noise. So let's say it was a sound signal, sound waveform, and I were to digitize it like this. Then instead of my original analog sound, now I'm introducing a little bit of noise in it. So if I do it very crudely, the signal you will hear would be very noisy. If I do it very finely, you won't. And in most cases, like our ears, for example, have certain ability to, like how weak a signal we can listen. So if once the bins are fine enough, no one will notice, right? So every system that you're designing would have some tolerance to how much noise it can tolerate, and that will generally dictate how many bins you need to have, and therefore what size of how many digital values you need to have, right? So this kind of analysis kind of goes on. Some signals you need to have many bins because of two reasons. A, we can notice tiny amounts of signals, and the other thing is those signals span large values. So, for example, people who make sensors that measure seismic waves, earthquakes. So in California, we have a network of earthquake seismic sensors. Those things usually divide things, and if you think in terms of like how many bits they use, 24 bits. That means the set that they have has 2 to the power 24 elements in it. And the reason is seismic waves have a large ratio of max to min, what's called as dynamic range. They can span a large range, and we often need to measure very tiny signals. Okay, so that's an example. On the other hand, for something like temperature in a thermostat at your home, you probably can get away with like 8-bit or something like that, right? So we don't need to be super accurate, and the dynamic range isn't a whole lot, right? I mean, temperature at home, maybe a little bit below freezing to maybe, I don't know, let's say -50 Fahrenheit to 120 Fahrenheit, something like that, right? I mean, we'll cover any place on Earth, for example. So applications differ, and therefore both these things, how often we sample and how many bins we divide are a function of application. Once we have done that, then as a digital system, every so often, I'm getting a value which is a value out of a discrete set. So now let's focus on the special case of binary value, which is really what sort of most of our actual computers operate at. Okay, again, not all, I must emphasize that. So binary basically refers to the fact that we have two values, and a lot of physical phenomenon are intrinsically two value. Like I had given the example of a door being open shut, and a lot of such things could intrinsically be two valued. So there, mapping between the real world and the bits that you process is kind of obvious. You still will have to make a choice which one is bit 0 and which one is bit 1, like is door open bit 0 or door close bit 0, but that's kind of just relatively inconsequential. Now, in other cases, we'll see that how we do it, but just to sort of go ahead, let's say I have a phenomenon which has 3 possible states. Okay, let's say, I don't know, I'm classifying heights of people into tall, average, and short. Okay, so I have 3 values. So then I'll have to have a set of 3. I'll have to map it into bits. So I can do it in a variety of ways. One possibility is I can say, you know, I'm going to represent everything with 3 bits. 001 would mean short, 010 means average, 100 means tall. Okay, so I could get away with that. I can do some other schemes. What's the minimum number of bits would I need in my example of 3 values to be able to represent things uniquely? How many bits must I need? 2, yeah. Right, so I can 2 bits give us four values, and I can kind of represent choose some 3 of 4. So given something which has n things in it, how many bits do I need? Anyone? Okay. No, not 2 to the power. No, that would be too many, right? It's going the opposite direction. So what's up? Yeah, log to the base 2 of it. Exactly. Strictly speaking, and then a ceiling function around it because it has to be an integer. Okay. So so now at least we know how we can take arbitrary number of discrete values and figure out at least how many bits, but I can certainly use more bits. And these different ways of coding have different names on it. Now, question is, why do we use binary values? And kind of the answer really boils down to is that usually there are a lot of physical phenomenon that exist which have 2 states, and so we can kind of use those things. So like, for example, switches are open or closed. I can easily take voltage high or low, right? I mean, ground or power supply, right? I mean, power supply voltage. Moreover, it's very robust to use 2 values. So even though voltage in my circuit may take, let's say I'm running a circuit using 5-volt electronics. Okay, so of course there's a spectrum of voltage, but if I just divide it into high or low, those things which are near 0, those things which are near 5, it's very robust. I don't have to worry about, let's say, if I were to divide it very finely and let's say 2.2 volt, but then maybe some noise from surrounding electronics perturbs it, then I'm in trouble. So it's much more robust to just think of the world in terms of 2 valued things. If you take things like voltages and try to squeeze more, divide it more finely, then you are more tolerant to noise, and we'll see that in a little bit what happens. So so what that boils down to now is that so again, our journey is we start with generally analog signals, we sample them, we discretize them, then I get at any given time instant a value which belongs to a discrete set. We somehow take that member of the discrete set, map it into some bit pattern, right? And we talked about that how you need at least log 2n bit bits in that pattern. And now we have to take these bits and we have to go back to physical thing, right? Because our computers are physical things, so I have to map it in something, and many phenomenon could be used. Of course, we will do it electrically, but you could imagine, like with those early examples I had, mechanical gear position, switch position, all those kind of things could be done. Okay, so these are some sort of some examples. Yeah, I have a link to the UCLA video, which I thought was pretty cool. I put it on the YouTube playlist. You can watch it. So now question we can ask is, okay, what if computer has continuous components, right? I mean, our transistors are not themselves discrete devices. Transistors using which we make our computers, they are unlike gears, right? Gears are intrinsically discrete, right? They have discrete sort of number of gear positions. So those are that's an example of in underlying physical computer is discrete intrinsically, but that's not always the case, and electronics are not like that. So if I'm working with electrical systems, we deal with voltages and currents, and voltages and currents are continuous. So I need to find some strategy of representing zeros and ones using these continuous values. And voltages are not the only example. I mean, there are computers which are like pneumatic computers. They use air pressure. There are computers which operate using other continuous things, like I have some examples out here, chemical concentration and all. So it's very common that many computing substrates, computing technologies are intrinsically continuous at a physical level. And so I need to have a strategy of mapping 0 and 1 into those continuous values. So that brings to our problem. How do I encode binary signals in those continuous things? And specifically for our purposes, how do I encode binary signals in voltage? So usually when you have digital logic, digital devices, they're kind of designed over to span some voltage range. It used to be like 5 volt. Nowadays, it's often 3 volt or 1.5 volt. It's kind of there in that ballpark. Our transistors need certain minimum voltage to do their job. It's a volt. If any of you have done a device course, this is the so-called threshold voltage of a transistor. Tends to be around nowadays, I think 0.6, 0.7 volts, something like that. And you need kind of twice of that. So that's where kind of 1.2 volt things you will see. Your Arduinos and all are usually 3 volt, 3.3 volt, maybe 5 volt. So those are the kind of voltages. So let's say I have a computer which sort of, as shown out here, goes from near 0 volt to some 2.0 volt, something like that. There's some span if you cover. So now the question is, what considerations come in when we are mapping 0 and 1 onto this continuous voltage line? So what can we do? Well, one strategy we could do is we can say, hey, you know, I'm going to do a line out here, and to the left of it is 0, to the right of it is 1, or vice versa, right? Now the problem out here is that if my voltage in the circuit was right out here, and then some noise affected the voltage, then it's very easy for 0 to be misinterpreted as 1. And that noise can come from a variety of sources. I'm sure you have encountered, like, again, if you're in E, if you put in an oscilloscope, you see kind of noise in the signal, but even at home and all, kind of you see crackling sound and stuff like that, right? I mean, our world is pretty noisy. There are all sort of electrical equipment. Anytime you run your microwave or dishwasher and all, the voltage on your AC line at home kind of jumps up and down, and these things then penetrate and gets into your computers. And if you monitor the voltage signal inside your computer, it's not stable. It's going to be. So there is noise, and so this noise can cause this kind of a problem. So clearly, this strategy of just some threshold, left 0, right 1, is not very good. So what we instead do is we kind of think of something more robust. So what we do is we define 2 thresholds. Okay, so we define one threshold out here, 0.7 and 0.7, 1.7. These are just arbitrary made up numbers out here. This would depend upon the specific component. And then what we can say is that to the left of it, to the left of this is 0, to the right of this is 1, and in between is not defined. And by that, what I mean is that a good circuit, a good digital system will never output a voltage which is in between. It may receive a voltage which is in between because that depends on the outside world. But again, if the outside world is well behaved, that shouldn't happen either. So this gives us a little bit of robustness now, because even if sort of things go into this middle no man's land, I can kind of recover. I can work with that. So actually, let me correct it. So VIL basically says that this is the maximum voltage I will receive for it to be considered a valid one. And VIH is basically saying it's the lowest voltage I will receive and still treat it as valid one. Okay, so that's how we are defining. So basically, we define this span now 0 and 1 with kind of this gap in the middle, which is designed to be give me robustness. It's kind of a margin, often referred to as a noise margin. It's basically saying I can tolerate that much of perturbation in this process. Okay, so what about too high and too low? Well, any circuit like this is going to have some sort of limit. So if the voltage goes too high, it will probably burn the circuit. If the voltage goes too low in the negative, when it goes negative, it can also damage the circuit, right? I mean, so there will be some limit which you cannot exceed in terms of just damaging the circuit. So our overall picture begins to look something like this, which is there is a max value, which really has to do with the safety of the circuit, or right? And likewise the min value, and then kind of in between we kind of divide it into this manner. Now this question, which kind of already attempted to answer, why do we have this no man's land in the middle? Because it helps us tolerate error. Okay, so basically small amount of variation. So like, let's say one system produces one value, it travels over some cable or wire or whatever, reaches the other system, and as it travels, it can pick up noise from the environment. So by the time it reaches a destination, it may not precisely lie in the blue regime, and so we can have at that point recover the signal. So digital systems has this property that noise doesn't build up, because let's say I receive a signal which is close to this value. I'll say, it's close to 1, so I'm going to still the transistor can kind of recover it appropriately. So when you look at data sheets of electric components, you will see this kind of stuff. Like, they will describe what their notion of 1 and 0 is. So let's say we are looking at this one. This is for probably one of the most famous chip in history, STI 7400. It has 4 what are called as NAND gates, which we'll see later. For our purposes, look at these things. So VCC is the power supply, and it basically says nominally it should be 5 volt, and it can be as low as 4.5, and it should be can be as high as 5.5. So this is saying something about the operating regime out here. VIH is the high level input voltage. So it's basically telling us that for the input side, as long as the voltage is at least this much, the circuit will think of it as a 1. Okay, so VIH is in this case 2 volt, and only the minimum value has to be specified. So it's basically saying as long as it's 2 or higher, I'm okay. VIL is basically on the 0 side. So it's basically saying as long as the voltage is lower than 0.8 or 0.8 or lower, I'm good to go. Okay, so you'll see these kind of things. Other parameters have to do with what temperature it can operate. So this thing is saying the circuit is good to go if as long as the ambient temperature is between -55 and 125 Celsius, actually. And I think Celsius, yeah, it's Celsius. Okay. So and so on and so forth. Okay, so so that's the that's the input side. Now the magic comes in is the promises it makes on the output side. Okay, so let me yeah, actually let me just, so you would also see that it has these two other parameters, VOH and VOL. And this is a promise that the circuit is making on what it is outputting. So in this particular case, it says that whenever it is outputting a 1, a high value, it will output at least 2.4 volt. And typically 3.4 volt. So now since it's outputting at least 2.4, and the circuit also said that as long as it's above 2 volt, it's a 1, that means I have a gap of 0.4, right? One circuit outputs certainly 2.4 or higher. And the next circuit says, as long as it's 2, I'm okay. So that 0.4 is the robustness margin that you have. Okay, that's the noise margin that I was referring to. And likewise, on the low side, VOL, it's saying that it will output at most 0.4 volt. And meanwhile, on the input side for this technology, we see that it says as long as it's 0.8 or lower, it will be treated as a 0, which means 0.8 minus 0.4. Again, I have a 0.4 volt of margin that I can tolerate. Okay, so essentially, if I'm connecting lots of chips of this nature, I can look at VOH, VOL of the transmitter, and we can look at VIH and VIL of the receiver and work out that in the wires connecting the two, how much noise can I tolerate and still work okay, right? The next stage will still correctly interpret 0 and 1. And so one can always kind of go back to the data sheets and all do this thing. For our purposes, what matters is the following, that digital circuits, actually, yeah. So digital circuits, unlike analog systems, have the following property. Noise does not build up. So if I have an analog system, every time there is some noise, that noise which goes through the next stage will make a noisy output. So if you take an amplifier in your sound system at home, if you feed it a noisy signal at the input, then the output on your speaker would be noisy. That's how an old type analog stereo system, or I don't know, nowadays again those turntables have come back into fad. So if you ever seen it, anytime there is a dust particle and all on the record, that will pick up and sort of come out in the output side. Digital systems, because of this property that I described, what happens is a noise on the input doesn't affect the output. It gets suppressed. So that's the nice part, as long as noise is lower than certain margin, which in my example there was 0.4 volt. So digital computers kind of essentially every stage cleans up the signal, right? It can accept somewhat noisy signal, but then effectively remove the noise, and the output is again back to a good signal. And that allows digital systems to cascade long chains of operations without sort of entering into a noise problem. Whereas analog things, if you cascade too many stages, the noise builds up. So the reason digital systems became sort of very used quite a bit, besides the fact we could integrate them and all, and they give us the software ability to program them, is also that they are very robust. Noise does not build up. If any of you have been following any sort of things which are going on in quantum computing are closer to being analog things, and their noise has again raised its head, in the sense that noise builds up, and one of the show-stopping thing there is that can we make quantum computing systems robust enough at low cost so that we can do computation on it. If we can't, the noise will swamp the performance and essentially make them ineffective. So key takeaway out here is this concept of noise margin, and the fact that as long as noise is below the noise margin, then every stage in my system sort of cleans up the signal. And so I can kind of keep building more and more complex systems. So it allows more complex systems. And that's a useful thing to have, naturally. So any questions on this part? Okay, so again, just to sort of repeat, so analog systems, noise on input shows up on the output. Digital systems, noise on input gets suppressed, output is clean. And the reason it is happening is, again, is the magic of this VIL, VIH, and VOH, VOL, which is we are more tolerant at the input, and then the output is again cleaned up. Okay, so that's what's happening. And I must emphasize that the specific values I'm using are just examples. Of course, it depends of the precise voltages and all depend upon the particular technology. So the kind of question you should be able to answer is, if I give you a data sheet, I can ask you, how much noise would be there, right? I mean, so you should be able to interpret VIL, VIH, VOL, VOH, and kind of talk about how much noise and all you can be able to do it. Okay, so what is happening now is that our outputs are more conservative, right? So VOL is less than VIL, so this is my noise margin, and likewise VOH is higher than VIH, so again I have a noise margin out here. So whenever I output, if it's a 1, I output value higher than what I'm willing to accept as a 1, and whenever I'm outputting a 0, I output a value lower than what I'm willing to accept as a 0. Yeah, go ahead. Pardon? Yeah, I mean, there's always certain amount of noise at which will go to the other side. Okay, so in this example, this gap, this is a noise margin. If the noise is very large, first I will go into the yellow regime, and then actually if noise is very large, I can go to the other side, right? Now, even in this middle zone, kind of things depend. You don't want to get into the middle zone because you don't have guarantees. It's possible that the circuit receives a voltage here, and it thinks of it as a 1. That will depend on the circuit. So you don't want to get into the yellow zone. Yeah.
So you said that when the noise is small enough that when it's in that small range, then it won't be counted. And then so in the previous example, you said that it's just the F of V1, right?
Yeah.
Now, if the noise was significantly large to the point where it did affect the output in the digital system, would it be F of V1 plus that noise, or the difference between?
No. It would be, so let's say it was V1 plus some noise. So since the noise is very large, so now you have to see how will the circuit interpret V1 plus noise. Okay, 2 possibilities. One is it will interpret it, continue to, well, 3 possibilities actually. Let's say you were trying to represent a 0, V1 represents 0. Your noise got added, so 3 possibilities. I'm still lucky, it still thinks of it as a 0. No promises, but it does. It's very high, in which case it flips to the one side. And the worst case is that it's in the middle and the circuit is now no more digital. It actually gets into a regime where it behaves totally weirdly. And in that case, suddenly your digital system is behaving like an analog system. And that happens too. Okay, so you can actually, I may have some picture or something, but essentially your digital circuits may get into a state where now they are neither 0 nor 1. Okay, and that's one term which is used for it is metastability. So it's kind of a failure. Your computer basically, yeah, it's dead. Like you have to kind of restart it. Yeah, let's see your question.
How are the noise tolerances decided? Because I noticed yesterday in my discussion, we went over for example, and V and L was different from V and H. Like, what is the reason for like maybe one of them?
Some of these things are historical choices, honestly, right? Because the thing is the following: when they select VIL, VIH, VOL, VOH, it's not simply they're making a chip. It's many chips, many different chips being made by many different manufacturers, and they need to be able to talk to each other. So some of these values historically were decided when, frankly, Texas Instrument, which was kind of the company we started out, and it kind of made these decisions. Why they did it and all, maybe some analysis of like how much noise is common and therefore acceptable there. Nowadays, within a chip, for example, and all, these are controlled by the companies, so it will depend upon how much they think they can get away with. So there's no like set philosophy about it. It will depend upon how much noise you expect and whether you have control over these voltage levels or not, right? You may have to comply with some standards, in which case you don't have any control. So someone raising the hand there. Okay. Anyone else with questions? Oh, cool. Okay, so digital signals are robust to noise accumulation. That's the nice part there. That unlike analog signals, where noise just keeps getting added, digital signals, they keep cleaning things up at every stage, and therefore I can create super complicated systems. Okay, so that's the nice part. So if I now remember that yellow zone, which the question here just sort of went after a little bit, that's a risky area. You don't want to get in there because all bets are off there. Okay, so once we are in that middle zone, anything can happen. So one way of looking at a digital system, if you're thinking in terms of voltages, is kind of like a transfer curve, that I have an input voltage versus output voltage, and this is what output of 0 looks like, and this voltage range corresponds to where the input is 0. And likewise, this voltage is when output is high, and this range is when input is considered high. And as you can see, that the output is more conservative, and that gives us our noise margin. So in this particular case, if I have a circuit like this, then what it's doing is it's flipping things, right? If sorry, it's passing the same thing. So if it gets a 0, it outputs a 0. If it gets a 1, it outputs a 1. So it's kind of an identity circuit of some form, right? I mean, it takes 0, outputs 0, takes 1, output 1. All it is doing is going to clean things up, right? It's going to get rid of the noise. This middle zone, this zone, is basically kind of like the no man's land. You shouldn't be there other than for some transient period of time. Voltages are, it takes some time for a voltage on a wire to switch because you have capacitances, and therefore some time, very short time, but still. So in this region, you are going to be there only for tiny periods of time, right? So only during changes. You are not going to be settled there. Imagine another circuit like this. Right? What is this guy doing? It takes a 0 and outputs a 1. And it takes a 1 and outputs a 0. So it's flipping the bits. And that's something referred to as an inverter, or a logical, if you're using 0 to represent true or false and 1 to represent true, then it's basically a not, it's doing a logical inversion. So, and any gate, I mean, you can think in terms of these, right? I mean, that it would have one or more input axes, depending upon how many inputs it has, and it will have one or more output axes, and you can define these things, how it operates. But important point that this gray zone in the middle, you're going to just pass through rapidly. You are not going to stay there, because while you are in there, the circuit is neither, the system is neither 0 nor 1. Okay, it's just some analog voltage value. And as I answered to the question a few moments ago, if the circuit outputs this value on a permanent basis other than this tiny amount of time, then the circuit has now suddenly gone into a non-digital mode, and you can't do anything about it. Okay, so now we know how to represent map 0 and 1 in terms of voltages. So now let's go back to kind of back up and think about, given I'm designing a system, how do I decide how to represent whatever information I need to represent in terms of ones and zeros, right? So we know how to represent ones and zeros in voltages. That part is solved. We kind of talked about earlier, given analog signals, how can I, given some whatever temperature or blood pressure or whatever, how do I map, like we digitize it? So we kind of talked about that. But now let's talk about what considerations go into when I have a set of discrete state of the world, how do I map it into bits? Okay, so easy case is that if I'm lucky enough and my system, whatever I'm trying to measure, has exactly the same number of values as my digital system. If it's a binary system, then anything which has just two values, door open, close kind of thing, that one is trivial. So for example, if I have a sensor which is detecting the status of the door, I can represent this output using 1 bit. So that's an easy case. Well, clearly one-to-one mapping, I don't need to worry about it. But more generally, that's not, more generally, that is not the case. So let's say I have pebbles or whatever, jewels of 8 different colors. So how do I represent something like this? And now here, kind of you get into this question of what do I intend to do with this, right? I mean, so firstly, going back to something I said earlier on, if I have 8 things, I need log to the base 2 of 8, 3. So I need at least 3 bits, right? Now, I still have many different ways of taking those 3 bits and mapping them to the colors. So that's choice number 1. Another thing is, should I be more extravagant and use more than 3 bits? That's the second consideration to have. So, for example, I have these 8 colors, and what I can do is I can okay, let's just take out here. So my apologies. So how many bits do we need out here? So as we talked about, I need at least 3 bits, right? So I can do something like this. I can say this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? I can map it this way. How many different ways I can map colors to 3-bit values? Anyone? Right, this is one way, right? But maybe I can assign 0, 0, 0 to red, right? So there are many different ways of doing it. So how many? Huh? 8 factorial, yeah. So there are 8 factorial ways doing this assignment. Okay, but this is what we will call as a most compact way of coding, right? I need at least 3 bits. I use only 3 bits. And this often is fine if you are short of memory. You want, okay, this is great. But in many applications, this may not be a desirable thing to do, because maybe I want to do certain operations on this information. I want to do something with it. And so there are many different ways of doing things, and that depends on the task at hand. So for example, a very common thing for something like this may also be, I may say I may use 8 bits. And then all bits are 0 except one of those bits. Okay, so like I can say yellow is 1 0 0 0 0 0 0. That is yellow. Red is 0 1 0 0 0 0 0 0, and you get the idea. I can create multiple such things. This is called one-hot coding. And there are other such common coding schemes which have different names. There is thermometer coding, there is gray coding, which I think the TS covered in the class. A bunch of commonly used ways of assigning bits to a bunch of objects, and they have different strengths and weaknesses. The most compact one is kind of the most compact one. It saves a lot of bits, but it loses sort of some strengths in other directions, and which we'll see in a little bit. Okay, so I think we have already answered these questions. I'm going to skip. Okay, so let's look at sort of an example. Let's say I have a thermostat which gets temperature readings from a sensor, and the readings are in the range of 68 to 82 Fahrenheit, and I need to have an resolution of 2 degrees Fahrenheit. So how would I represent it? So 68 to 82. So yeah, let me just come. So essentially it's two steps of 2. So 68, 70, 72, 74, 76, 78, 80, 82. So we discretize the domain. So kind of usually given your specification, some of this will be natural. Now we encode the values. So how many bits do I need? Well, here I have 8 things. So I'll have to, I can again get away with 3 bits, right? So I can do this kind of a mapping, right? Now, this way of mapping 3 bits has the advantage that if I think of these 3 bits as a binary integer, base 2 integer, then I can easily do comparison, right? 111 is more than 000. So if the temperature says 111, right? I mean, my circuit says 111. I know it is 111 is more than 000. There may be a different shuffling in which this property may not hold true. So sometimes you may have to think about what operations do I want to do in a thermostat. What kind of things? Like usually a thermostat will compare ambient temperature with the set point, and then take the difference, and then use that difference to drive your furnace or AC unit. So probably a thermostat, we want to be able to find difference between 2 temperatures and map them into some sort of a control command for my AC unit. So in this particular case, that makes sense. In my previous example of stone colors, that was not necessary. I don't know what yellow minus red has any value, probably nothing. So much like if you have done a software course, when we design data structure, we kind of think about what operations we are going to do. The same thing out here. A good way of encoding is one which makes the operations you want to do easier. So you always have to think about what are the needs of my application, and then pick a good encoding for that. Okay, so there are many ways to represent information. These are some other examples. So this way of doing things, so 68 is all 0, 70 is 0001, 72 is 00011, and so on and so forth. This is called thermometer coding. Why do you think it's called thermometer coding? Anyone? Yeah, exactly. The old mercury thermometer, right? I mean, the kind of rises with temperatures. This kind of looks like that. So thermometer coding. Okay. In this particular case, you can say again, maybe counting the number of ones is easy operation, and therefore I can easily tell how many, which temperature is more, right? I mean, I can say 000, whatever, something with 4 ones like this is more than the other. There is also a little bit of some other properties out here, right? I mean, let's say there was some noise, and this signal flipped to 1101111. Let's say flip to this. Am I right? 1 2 3 4. 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Yeah, let's say the bit flipped. I immediately know that this is an incorrect thing, right? It's not a feasible value, and therefore I can correct it. As long as if I make an assumption that at most one bit can flip, then I can correct this thing, right? So I can detect errors and correct them. That's not the case out here. If let's say 111 change to 101, well, that's a valid value too. And so this way of coding has no way for us to detect an error happening, let alone correct it. Whereas this way of coding, I can detect certain errors, not all errors, like I cannot detect all zeros becoming 0001. So I can't. So extra bits, one of the, besides making some operations easier, perhaps, they can also help give you robustness, because they're giving me an ability to detect and correct errors, right? So extra bits can provide error detection and correction. And that's a very important role they play. And there's a whole field called coding theory, which deals with this part. It deals with how to represent things compactly and how to represent things robustly. Our communication systems, our memories in our computers are all designed for it. If you have ever purchased DRAM for your computer, then you can buy DRAMs. DRAMs come in these sticks and they are designed for 8 bits, but sometimes they come with a 9-bit DRAM with an extra bit whose purpose is to help detect and correct in the computer. So that's the role of these extra bits. So different ways of representing, again, have information. Now, of course, the disadvantage out here is that I'm using more bits out here to represent the things, and also it's not clear that this is the best way to provide robustness. Some other examples. This is the one-hot representation. I'm now using 8 bits, and the which bit position is one tells us thing. So many different presentations. Okay, so you can think one can think in terms of, again, like, what are my costs and what are the advantages that are coming with it. So sort of there's nothing terribly deep about these representations. A lot of times their pros and cons are kind of obvious, but kind of one needs to reflect. Don't just kind of jump onto a representation, because it can make subsequent tasks easy or hard. So for example, in fewer bits, more bits, even more bits, easier to compare, even easier to compare, and here easier to detect bit errors, and so on and so forth. So that brings us to, how do we choose encoding? Well, let's take an example. Let's say I'm designing some sort of system where we need to deal with dates, right? Calendar dates. So how do we encode a date, right? In a programming language, if you're familiar with Python, you can like print date, what is today, in many different ways, right? I mean, there are many different formats, or even current time, there are many different formats. Okay, so how do we encode? So a common approach is that we think of a base date and then compare the number of days from that. So like I can say base date is, now this is rubbish, but that's what the book uses. Why is this bad? Why is this base date wrong? Anyone? Huh? Yeah, there's no year 0. There's 1 BC and then 1 AD. There's no year 0. Okay, but our textbook is littered with silly things like this. So okay. So firstly, there's a base date. Let's say January 1, and let's say there was a January. Let's say there was a year 0. Okay. So how many bits do we need? Well, I can, as I'm picking this thing up, we can kind of think of like, okay, we are in the year 2023, and maybe we are care about our system for the next century or two, and then kind of work backwards from that and say how many bits will I need. So if it's year 2020, then 365 roughly, 365.25 roughly. So 20 bits, maybe we need another bit or two, another bit to just give us some longevity. But I can, so sounds like around 20 bits, 21 bits should suffice for us. So we could work with that. The problem with that representation is I can represent each day uniquely. I can do it. I can say which day was this date earlier than another date or later. I can compare the numbers, but I can't really tell you, given a particular 20-bit pattern, which year it was, which month it was, which day within the month. You'll have to do some thinking there. Okay. So to make that easier, I can create a data structure, right? I can create something which has 3 fields: month, day, and year, and represent each one of them separately. So now how many bits do I need for month? 12 months, 4 bits. How many days? Maximum 31, so 5 bits. And so that's 4 plus 5. And then how many years? Well, we're looking at the year 2020 something. So how many bits do we need for that? One can sort of work that out. Again, in this particular case, ignoring kind of the future part, we again need 20 bits. So we have 20 bits. Comparison is some operations like which month it is, which day in the month it is, which year it is, now have suddenly easier, but we have not kind of lost a whole lot of like we are similarly compact. We can't tell you which day it is. Probably talking about which day of the week it is would be easier in this representation, the first representation, and the second one, I can just do a mod 7, whereas here I'll have to do some look at the year, right? I mean, I'll have to do some computation. So easier day of week. So if I expect day of week to be a common operation, I should either pick this, or I can explicitly add another 3 bits to do day of week encoding. So I could do that. So I can do a separate day of week, but in that case, there is redundant information, because day of week can in principle be computed using the other 3 fields, but it just makes an operation easier. You probably make these kind of trade-offs when you are designing a software program also, no different out here. So when you are faced with any sort of a design problem, one of the first thing is, how shall I represent information? What will make my hardware easier or harder to do? That's kind of logic. Let's take another example: cards. Okay, playing cards. So how to encode playing cards, right? I mean, in many games, I mean, nowadays there's software which let you play poker, bridge, stuff like that. So internally, clearly, they must be representing cards somehow. So typical American or whatever playing card deck has 52 cards, 4 types of cards, 13 cards within each suite. There are 2 jokers, right? I mean, that's a standard playing deck, but let's ignore the jokers. So I can number each card in some sequence, right? I can order them, and there are 52 cards, 6 bits. I can give each card a 6-bit number. And I can, the problem is, it's probably not very useful, because in most of our games, there are complicated rules about which card is more powerful than another card, right? I mean, some games, numeric values, and then if the numeric value is the same, then the suite color, that matters. So not very easy, but that's very compact. I can do suite plus number, right? So that can help make some comparisons which are typically encountered easier. Again, 6 bits, but arguably a better strategy in this case. Now, in many cases, in many games, I may also need to represent more complicated structures, right? Like, for example, in some games, they define hands, and a hand is superior to another hand. So maybe I might want to represent entire hands in this case. So if I have a 5-card hand, one way I can represent them is I can say, okay, the 5-card hand is nothing but a set of 5 cards, and I already know how to represent cards, so it's just a set of those 5 things. But then operations like, is this hand superior to this other hand, those become difficult. So I can now begin to go into representing hands explicitly, and now we can talk about how many different 5-card hands are there. So many, okay, and then that requires 22 bits. Maybe I may want to represent that separately. So these are kinds of considerations that come up. Again, the analogy I'll say is with software, that whenever you're writing a piece of software, you think in terms of the very first thing you have to do is, what are my data structures? It's the same thing out here. You have to think about how do I represent the necessary information so that everything else becomes simpler. So, few things to realize. One is the most compact is normal, generally speaking, may not be the best thing to do. And secondly, you need to think about what operations you want to do with it in order to decide. So there's no one best way. It really depends upon what operations you want to do. And so spending some time on it sort of pays off quite a bit. So goodness depends upon what operations are commonly done by your system, what representation would make implementing those operations efficient. And we'll see as we go along, kind of, there are many, like what defines the efficiency of implementing, what will make it easier to identify that some error happened, what will make it easier to your system to be more robust, and also those kind of things. So so let's look at some examples. Okay, so let's say we are doing calendar, and we have 3 different ways of doing it. I can represent as a 9-bit number between so 1 year. Okay, so I can represent as 9 bits. I can represent month and day of month, or I can represent this as month, day of month, and day of week. And we can examine, let's say I want to say, I give you one, so I have 9 bits here, I have 9 bits here, and I have 12 bits here. So let's say I give you the bit representation of today, and I ask you, what is tomorrow? What is the bit representation of tomorrow? So with a 9-bit number, it's easy. I just add 1 to it. With the 4 plus 5, it's a little bit harder now, right? If I add 1 to the 5-bit for the day of month, but then I may have a rollover, right? Because we will be in the last day of a month. So in that case, I have to increment things. And then 4 plus 5 plus 3 has kind of a mixed attribute. So one could imagine that easy, kind of easy, but somewhat harder, and easy. So I would kind of put it as all 3 are easy, but within that easiness, like the latter 2 are a little bit harder. What about determine if 2 days are in the same month? So which one do you think is, what about, let's start with 2 days are in the same month? Easy, right? Because we have an explicit month. Easy. This one is tricky, right? Because just because the gap is less than 30 or 31 or something like that doesn't mean they're in the same month. So you'll have to actually, so this one is not easy. So hard, easy, easy. Okay. Determine if one day comes before another. So in this particular, so in this case, kind of easy-ish. Okay, so determine if a day is a particular day of the week, right? Hard, and this one is easy. Okay, so the point, I guess, basically just from takeaway out here is the following: that depending upon the representation, operations become easy or hard, and one just has to be aware of it. And sort of oftentimes what may happen is that right near the input of the system, you convert the representation into something that is easy to work with. Like, for example, let's say I'm going to do a lot of multiplications of a bunch of numbers I'm receiving. And multiplications are generally considered to be harder than addition. So what would you do? Anyone? Yeah.
Store the log.
Yeah, you can do a look up in a table, get the log, and then stay in the world of log, do your multiplications, and go back, right? So sometimes just thinking about kind of going to a different representation sort of helps a lot. So to summarize, I guess takeaway from sort of this module is how we represent information matters, and so spending some time about that kind of can help things in general. And earlier on, kind of we talked about that there are ways in which we can discretize real world analog values without losing without a deleterious impact. And moreover, I can represent zeros and ones, or more generally digital values in terms of things like voltages, and do so robustly. And probably the biggest takeaway from today's this particular module is that digital systems have this whatever property of self-renewal, right? That is, every stage cleans up the signals. So unlike analog systems where error builds up, here kind of every stage cleans up the signal so that I can cascade large numbers of them to create very robust signals. Okay, so this is end of this module. Let's take a couple of minute break while if you guys have any question. How about 5 minutes? This is so to be meaningful. And if any of you have questions, feel free to come by out here. And then we are going to start on the next topic. So 5 minutes. So right now it's 5:20. So we start at 5:25.
I was wondering a bit about the noise margin. Is that just something that you want to keep small as possible? And I was having a little bit of trouble sort of.
Yeah, no, you actually want large noise margins, right? Because that would be more robust. The problem though is if your noise margins are large, then that means you are going to increase your voltage, the span of the voltage, right? And if you increase the span of the voltage, that means your signals are swinging more value. And unfortunately, power consumption depends upon how much the signals swing. Okay, so and actually also generally, as we have been scaling technologies to tinier sizes, the voltages are going down. The reason they go down is because if you keep the voltage same and shrink the size of the transistor, then electric field goes up, right? Electric field is voltage divided by distance. And if electric field goes up, then my transistors are getting intuitively stressed more, right? They're being subjected to a higher electric field. So usually as transistors have been shrinking, so has the voltage been to keep the electric field constant. And so now that forces us noise margin to be smaller. So there's a complicated trade-off that therefore results from that. Yeah. Okay.
Thank you.
Sure.
I was wondering, you mentioned the Shannon microsecond. Suppose we get like some unknown signal, we don't know like how high the frequency is, and we want to do some sampling.
Great question.
Some fixed rate.
Guarantee
how much the error will be?
No, unfortunately not, right? So what happens is there's a phenomenon called aliasing. So let's say you are wrong about what the maximum frequency component is. So then so now you are sampling at something which is less than 2f max because you didn't know the correct f max. So then something called aliasing happens, where basically there's kind of a signals from higher up, they kind of map back. So actually, like how in movies and all you see like the fans rotating in the reverse direction. That's an example of aliasing. Okay, so what is happening is that the movie is taken with a particular frame rate, which is lower than the wheel speed, and so therefore the wheel appears to go back. Okay, so unfortunately, when aliasing happens, in some cases, if you know other things about the signal, maybe you can still undo the effect of aliasing. In general, you can't. So the trick is in electrical circuits, we put an analog filter to remove the signals above what I am designing for. So I may say, the signal I will assume has no more than 100 hertz, let's say. Okay, and then I will put an analog filter to remove anything above 100 hertz. And that will come from experience / prior knowledge about your signals. These filters are called as anti-aliasing filters precisely for this reason. So they're kind of designed to just get rid of signals above. Okay. Thank you. Okay, let's resume. So we saw in the material thus far on how to represent information. Now we're going to get into really what's the crux of what this course is about, which is how do we process information? How do we process information digitally, right? So so somehow someone has taken care of taking the signals into digital domain. Someone has taken care of sort of structuring that digital information appropriately in light of operations we plan to do, and we are given some way of mapping things into voltages, and therefore we have circuits which can do operations. The question is, what operations should they do? So voltages and all, we are basically not going to witness against in this course. From now on, it's more about kind of like at an abstract level of like, you know, what operations do we need to do? That's why it's called logic design of digital systems, right? So we are going to think in terms of necessary logic. Okay, so in particular, we are going to introduce two types of processing that exists in digital systems: combinational logic and sequential logic. And we are going to look at some examples of that. And then we are going to look at how do we take complicated things, decompose it, and we're going to look at what are those primitives, which are referred to as logic gates. So that's the part we're going to look at. Okay, so combinational logic. So fundamentally, you can think of digital computation, okay, whether hardware or software, really in kind of broadly into two categories. There are things which are combinational. And by that, what I mean is, think of a box. It has input, it has output, and output only depends on the current input. So output at time t is a function of the input at time t and nothing else. Okay, if I change the input, the output will change, maybe with a little bit of a lag, depending upon the circuit delays. But at least in an idealization, you can say, if my circuit was infinitely fast, change the input, output changes, reflects that. Okay, so and this doesn't depend on, obviously not on future, but also doesn't depend on the past. Okay, so that's combinational. And sequential, the output depends not only on the present input, but also on inputs which happened historically. Okay, how much in the past depends, but they at least depend upon at least an input at one instant in the past. Okay, so that's sequential. And so just to give you an example, let's say I have something like this, which is kind of like a crude simplistic thermostat. So I have a temperature sensor which is giving me the current temperature. There is a preset temperature which the user sets, and then I have some sort of box which compares the two values. And if current temperature is higher than the preset temperature, then it turns on the fan, okay, essentially in an attempt to cool things down. So what do you think it is? No. So again, I'm asking whether this guy is combinational or sequential. Right. So it is true that user set the temperature in the past, but at the current moment, input B is whatever the user set. You're right. I mean, the user may have set it in the past, but insofar as this box is concerned, current value of B is this, current value of A is this. And all it is doing is a comparison operation, right? If the user were to change preset temperature, this thing will change accordingly immediately, right? So the output in this case is strictly a function of current value of A and current value of B, not what we saw previously. If let's say there was a user who was continuously changing the preset temperature, then it would be more clear that this thing is behaving without any memory, without any dependence on the past. So this example would be one which one would consider as combinational, that insofar as my digital system is concerned, its output is strictly a function of the present value of its two inputs, in this case A and B. Okay, so essentially in terms of a software function, you can say it's like a function which has no memory. It doesn't remember anything in any static variable or any other global variable, okay, depending upon your programming language, or for that matter in a file or anything like that. So operations like arithmetic operations, A plus B, A minus B, A greater than B or not, those kind of things, they are all examples of combinational things. There is no memory of the past. So that's an example. Yeah, okay. Let's so in this particular case, let's say again, so we'll go through that whole cycle of like, we have to figure out how do we represent current temperature, how do we represent the preset temperature. So let's say there are 4 possible values of current temperature, 50, 60, 70, 80. We can represent them using, let's say, 2-bit values, 0001, 1011. And 4 values for preset temperature, again same way, 60, 65, 70, and 75. And so those are the preset temperature, and then we can design our system. So we'll have to design our system, this compare system, which takes 2 2-bit numbers and then outputs a 1 or a 0 for controlling the fan, depending upon whether A is greater than B or not. So, okay, so now what this system is doing is saying, if current temperature is higher than preset temperature, set the fan on. So the equation that we are really implementing in this is fan on is current temperature greater than preset temperature. This is, think of it as a Boolean operation which outputs a Boolean value, right? So is current temperature greater than preset temperature? And if it is, then fan on is high. And if it is, if current temperature is equal or less, then the output would be 0. In a programming language term, you can say it is really implementing this operation. I don't know if you've seen this operation in programming languages, but it's kind of like that. So you can think of it like that. Or in many cases, it's just that this is outputting a Boolean value thing, so it's going to fan on. So that's what this system is doing. We can represent the operation of the system any different ways. There are many different ways you can think about it. Here we did it as an equation, kind of inspired by what programming languages do. But there are other ways of doing it. I can express it as a table. I can just list all possibilities of inputs. So we have 4 current temperature values and 4 preset values. So there are a total of 16 possible values. I can have 16 rows. And then for each one of them, I can say whether the fan is on or not. So something like this is what often referred to as a truth table. It's essentially kind of listing all the values, all possible input patterns that are valid, and then the corresponding output pattern. Oftentimes in math also, or computing, we kind of list things like that. In computing, we'll call it a lookup table, right? I mean, we kind of just pre-populate an array or a table in these terms. So now truth table is one. Another possibility is that maybe there are some building blocks, and then anytime you give me a description, I can use those building blocks, wire them up, and I can have my circuit. And in fact, this is what computer scientists and electrical engineers call a circuit, right? Logic circuits. I can create circuits using gates. By the way, lest you think that circuit is a term only E is used, that's not the case. All of CS theory has a notion of circuits also. They literally call them circuits. Okay, so now let's go back to the truth table formulas. So truth table, kind of the idea is that we list all possible input patterns that can occur, and then for the output, in our case, there's only one output, and it's a 1-bit output, right? Fan on off 1 0. I kind of list all those possibilities, so I can kind of fill it out. So I'm just going to sweep through these. Okay, so yeah, so I can so some of these are marked as yeses because current temperature is higher, right? So here, and these values. Sorry, not this. Okay, so in this particular case, there are 6 rows where output is 1, and the other places output is yes, and the other places output is no. So I can do this listing. What's the disadvantage of truth table? As opposed to an equation.
Very compact.
Yeah, it's not very compact. I have to write a lot, right? And if I have to write a lot, that means in a computer I have to store a lot. If I have n input bits, if all the inputs that I have add up to n bits, how many rows will I have in my truth table? Yeah, so how many? Huh? Nope. N bits. So in this case, I had 4 bits, 16 rows. So n bits, how many? How many different things you can represent with n bits? Actually, someone here had given an answer long ago when the answer was log to n. This is the reverse. This 2 to the power n, right? 2 to the power n rows, right? If I have n bits, then I can have 2 to the power n possibilities using those n bits. So my truth table can have 2 to the power n rows. Okay. Let me ask you another question. In this problem, the output column, y is here, and these 4 are y, right? So there's a one particular output column. But maybe I may have a different, let's say I were to modify this policy and I were to say, if current temperature is greater than or equal to preset temperature, then turn the fan on, right? So in that particular case, this will become a y. This will become a y. This will become a y. Right? So 2 more y's. That would be a different, slightly different logic, a slightly different thermostat. Okay. So you can think of it as it's representing a different equation, a different function. Right? So each truth table corresponds to an equation. How many different truth tables of 16 rows exist? Or equivalently, how many different equations exist that the truth table are represented, right? I mean, you can think of it as a mathematical function. It's taking input and mapping it to a particular way for the output. The question is, how many different truth tables exist where you have 16 rows? Huh? 2 to the power 16, yeah. So because I have 16 rows and any one of them could be yes or no. So I have 2 options per row, so to the power 16. Okay. And we just talked about that if I have n bits of input, then I have 2 to the power n rows. Right. So if I have a digital combinational system function with n input bits, then how many distinct digital systems exist? Well, they have 2 to the power n rows and 2 to the power n possibility, right? So that many distinct digital systems exist for n input bits, right? Some of them are trivial, right? It always outputs a 0, always outputs a 1. The point is that many distinct things exist. So in particular, let's say n is 3. So if n is 3, then truth table has 8 rows, and the final column can be done in 2 to the power 8 different ways. That's 256. So there are 256 different functions there. Okay. So yeah, so I mean nothing terribly deep, but you should be comfortable out there. So again, a particular truth table corresponds to a particular equation, and as many equations exist possibly for those inputs as the number of distinct truth tables. Truth table are not very compact because the number of rows are going exponentially. Let's think of it this way. In your computers, earlier on, we talked about that our modern computers have 64 bits values, right? So let's say I have 2 variables, X and Y, each one of them is 64 bit. So I have 128 bits. If I'm doing an operation over X and Y, let's say X plus Y, X minus Y, X multiplied by Y, right? I mean, so these things take 128 bits of input. So the truth table there would be like if I'm trying to describe the truth table of a adder which adds 2 64-bit numbers, how many rows will it have? 2 to the power 128, which is roughly speaking 10 to the power 40 something. That's hell of a lot, right? Very soon you begin to get into more than the number of subatomic particles in the universe and those kind of things. Okay, so clearly truth table is not a good way to represent realistic systems, because already if with just for 64 bits we run into those problems. I mean, just think of like the kind of stuff that exists in our computers. But as a concept, it's good to think of it this way. Can you represent these things more compactly? Any ideas? Like, is there a way that instead of 16 rows, I could get away with fewer rows? So, anyway, yeah, go ahead.
Yeah, an observation, whenever the current temperature is 80, it's always yes, and whenever the current temperature is 50, it's always no.
Okay, so great observation, and we'll rely on that in lectures to come quite a bit. I guess I was looking for just a simpler answer, which is, maybe looking at this, there are a lot fewer yeses and nos. I should just list the yes rows and nothing else. Okay. And likewise, if it was the other way around, there were a lot fewer no's, I will just list just the no's and can say everything else is a yes, right? So there are ways you can do some compactness, but that depends on the function. Some functions are pretty evenly distributed, right? I mean, there are some functions where half the values are yes and half the values are no, right? I mean, and there my strategy won't work, obviously. Okay, so truth table are not a desirable way if I were to reason about digital computation, right? I mean, they're just way too verbose. But having said that, still it's a good conceptual exercise, and for the kind of problems that we often at least encounter when you're learning about digital systems, I could certainly get away with it. So this was my truth table as written in terms of the natural description of the problem. I can map everything into bits. So I can, yeah, I'll just move forward, okay, rapidly here. So I can just write down the equivalent by bit representation. So I can basically say if input is 0, 0, 0, 0, output is 0. If input is 0, 0, 1, 1, output is 0, and so on and so forth. Okay, so going from here to here is just mechanistic, right? You just replace everything by the binary representation. Okay, so now let's imagine I were to modify this problem and I say that, for preset temperature, maybe there are only 3 possibilities. So I eliminate that preset temperature cannot be 75. So 1, 1 disappears. So in this particular case, 4 rows get scratched, right? They cannot occur as per our problem specification because preset temperature can never be 1, 1. So those 4 rows can never occur. So the question then becomes, when you are designing this system, if the input B is 1, 1, what should I do? My problem specification said it cannot occur. So in my truth table for those rows, I don't know what to put in the output, right? It's fan not on, fan on or off, right? I mean, what should I do? So this is where it kind of gets into your perspective. So one stance you can take is you can say, if an input value which is not supposed to occur occurs, I don't care. I'm going to pick whatever is more convenient for me. So literally, I can say on these places, I can say don't care. If the output is 0 or 1, so be it. The other possibility is in this particular case, you can say, this is controlling a fan. There is some cost to it. So the safer choice would be to keep the fan off. So it's kind of like depending upon the thing, you can either pick a safe choice. So that's option 1. And option 2 is safe choice. That depends on what the problem is. If it's a car, probably the safe choice is to stop the car as opposed to speed the car or whatever, right? I mean, so it will depend on the problem. Usually, in courses like these, we kind of say, don't care, you can pick any value. Okay, so that means for those 4 rows, whatever leads to a more efficient design, you can pick that. Okay, so these things, I need to figure out a better way of managing this thing. Okay, so the stuff which has a question mark are the one where, like I said, you can view them as don't care, or you can say I'm going to pick safe values. So out of specification values, don't cares, we kind of list a D there. Sometimes it's an X, sometimes a big D. Okay, so there are a variety of different ways they are represented, but kind of the idea is that for things which should not occur, I don't care, I'll pick whatever makes it easier to design. So combinational logic is basically, you can think of it as, now stepping back, bunch of inputs, right, and bunch of outputs. In our example, there were 4 bits of input. There were 2 2-bit inputs, total of 4 bits, and I had 1 output of 1 bit. Okay, in general, I will have a bunch of inputs, each one of them certain number of bits, and a bunch of output, each one of them with certain number of bits. And essentially, what combination logic is doing is implementing a function. Output is a function of input at the current moment. So you can basically, actually more strictly, you can say output at time t is a function of input at time t. Okay, it's strictly represented. There's no dependence on the prior values of the input. Okay, so that stands for combinational logic. So very crucial part, it's memory-less. Okay, it has no memory in the past. So more compactly, oftentimes you will see this notation. It basically says that I have an input with n bits. Okay, so it's saying n bits, and it's saying output m bits. Okay, so the truth table for this, you can say will have 2 to the power n rows, right? Because I have a total of n bits of inputs, and then I will have m output columns because I have m output bits. Okay, and for each one of them, I'll have a 0. So in this particular case, you can say I have 2 to the power n rows. And then for the output, well, each column, each of the m columns can have 2 to the power n different ways of doing it. And each column can have so many. So you can say all of this multiplied m times to the power m. That many functions are possible of this type, that many combination logic. So things grow very rapidly, but I mean, it's a main part is to remember is memory less in our case. So yeah, let's see. So yeah, I think yeah. So again, just to recap in the remaining few seconds. So combination logic depends only on the current input, no memory in the past. We can express it as a logic equation. We can express it as a truth table. We can express it as some sort of a software pseudocode. There are a variety of different ways one can express it. Common to all of them is the fact that the current output depends solely on the current input. So we are going to go into sequential logic on Monday.